So let's say we had something like, we're writing, I think they said like u equals x to the z over y. Or I think it was y over z, but I'm going to change up a little bit so I'm not actually doing the homework problem. And so we're trying to find all the partials. Del u, del x, del u, del y, del u, del z. So if I'm trying to find del u, del x, I'm thinking of z over y or anything that's not x. That's just a number. So like, for example, that could be 5. And I know that the derivative of x to the 5th is 5x to the 4th. So the derivative of x to a number, I think, is going to be that number times x to that number minus 1. Right? Just like, I love whether y instead of a j. Just like if u equals x to the 5th, du dx is 5 times x to the 5 minus 1. But again, right, we have to get ourselves in this mode of thinking of, oh yeah, right, this is everything else that's not the variable of interest is acting like a constant. Let's look at del u del z next. Actually, I think that's the one's going to be a little bit easier to deal with. So now I've got, so I suppose I should say, when I look at u equal x to the z over y, I'm imagining, well, everything except for z is a constant. So I'm thinking of something like 6 to the z over 2. That's kind of what I'm thinking about taking the derivative of. And so when I do that, 6 to the z, or how do we take the derivative of 6 to the z? That's most of it, but then there's a little bit more. So in general, if you're taking the derivative of e to the x, it's e to the x. If you're taking the derivative of a different base to the x, like 6 to the x, it's 6 to the x times the natural log of 6. So that's kind of the rule that we have to apply here, is that we essentially have 6 to the power. We have an exponential function. Welcome, come on in. We're just talking about a problem similar to homework problem 9. I don't remember. This is section 9.2. Well, this is also 9.3, right? You guys have both sections due on tomorrow. But I think we're looking at one like 9.2 number. I was looking at all of them earlier. I don't know. I don't remember the number. I do remember now. I know exactly where it is. It's actually no.
I think it's just 9.2.
Well, which problem?
It is, I think 30 or 28.
Oh yeah, you're right. Yeah. So the problem is similar to problem 28 from that section 9.2. So we're talking about how if you're taking the derivative of something like x to the y over z, if you're doing the partial with respect to x, it's kind of the most straightforward case in that you've kind of got like x to the 5th, and the derivative of x to the 5th is 5x to the 4th. So the derivative of x to this number is that number times x to the 1 less number, right? Just using the power rule essentially. But for this part here, where you have the partial with respect to z now, we're saying, well, I have like x to a power. Come on in. You're fine. Oh, I'm leaking water everywhere. So just to catch you up as well, we're looking at a problem similar to problem number 28 from section 9.2. So we just talked about how if you have u equal to x to the z over y, if you take the partial with respect to x, it's kind of like having x to a number. And the derivative of x to a number is that number times x to the 1 less. So over here, we're getting that number times x to the 1 less number. But now we're trying to take the partial with respect to z. And that's a little more complicated. I'm trying to, I need to bring my napkins with me or use it. Or really just use it for water bottle. This one kind of leaks sometimes. Let me wipe up the water cooler. Okay. So if you have something like this, there's this rule for exponential functions where the derivative of 6 to the x is 6 to the x times natural log of 6. So if I've got the derivative of x to the z over y, I'm thinking the derivative, the partial with respect to z is going to be x to the z over y. That's almost always the case. If you're taking the derivative of an exponential function, you always get that same, exponential function back. But then there's two things we have to consider. One, we have to multiply by the natural log of the base. And two, we have to apply the chain rule. The derivative of 6 to the x is 6 to the x natural log of stuff. The derivative of 6 to the, say, x cubed is 6 to the x cubed times the natural log of 6 times the derivative of the exponent. So over here, we're taking the derivative of x to the z over y, we're taking x to the z over y times the natural log of x times the derivative of z over y with respect to z, of course, because that's the partial we're doing. So then we're going to get x to the z over y times the natural log of x, and the derivative of z over y with respect to z is just 1 over y. Because you can think of that as 1 over y times z, and its derivative is 1 over y. So if I were writing this, I would probably leave it like that, but you could write it all like over y if you wanted to. So now for the hardest one. It's actually not that much harder. So del u del y is going to be very similar to del u del z. It's the same idea. I've got x to the stuff. I've got x to some function of y. And the derivative of x to the stuff is going to be x to the stuff times the derivative of the stuff times the natural log of the base. It's just that here, the derivative of z over y is going to be different. And here, the derivative of z over y was 1 over y because we were just taking the partial with respect to z. Here, I would probably rather think of that as z times y to the negative first and take its derivative as, so x to the z over y times the natural log of x times the derivative of z times y to the negative first with respect to y is going to be negative z times y to the negative second. So those are the different partial derivatives of this function. It's a little tricky. It's especially tricky because when you see like that x to the power, when you're not taking the partial with respect to x, it's kind of weird to think of it as an exponential function. But it is, it's acting just like 6 to the x. Questions about this one? It's a good question. Let me grab my papers here. Yeah, okay, good. Is that just me? Oh yeah, it's just me. All right. So let's continue talking about partial derivatives, and then we'll talk about some tangent lines. Also, before I forget, I have a handout for you all. This is actually problem number, it's not due, but it's problem 9, section 9.2, problem 3 from your homework. So this will definitely give you some good intuition and direction on how to do this problem here. I forget which problem this is. Number 2. This problem is very similar to problem 2. I would encourage you to, not right now, but later on, if you're working on problem 2, use this as kind of a guide. He also did a similar problem in class with a heat index, I think. So those are both good examples, and I think they're worth looking at. The problem is a little weird, but they're really just asking you to kind of go back to your 17A roots and say, I know I can estimate a derivative by doing the change in the function divided by the change in the input. That's really all that problems ask you to do. It's just kind of confusing to read the table. So I think that handout will help you do that. I certainly found that problem confusing the first time I looked at it. Let's look at, let me see here. Now let's look at one or two more examples. Let's say we had this function here. X over x minus y. And we wanted to find all the partial derivatives. And when I say all, there's a specific list of 5. I mean, the first derivative with respect to x, the first derivative with respect to y, the second with respect to x, the second with respect to y, and then the mixed partial. Those are usually all the first and second derivatives. And they do they are important. They help, we use them all later on to calculate whether we have a maximum or a minimum somewhere. So that's kind of why we're focusing on those ones specifically. So if I want to find the first partial with respect to x, I'm going to use the quotient rule. It's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. And since I know I'm going to take the second derivative at some point, it's definitely worth my time to simplify this as much as possible. So simplifying, I get x minus y minus x, so those x's cancel, over x minus y squared. So I would say that's negative y times x minus y. Oops, not times. I got ahead of myself there. It's negative y divided by x minus y squared, which I might find convenient later on to think of as negative y times x minus y to the negative second. Let's find the first partial with respect to y. This one's actually, I really don't need to use the quotient rule here. I might prefer, oops, sorry, yeesh. So I wrote something kind of wrong here. That's not my first partial, that's the original function. I should have really written f of xy. I shouldn't have really written it again, but I want to rewrite it as x times x minus y to the negative first. So that then I can just take the derivative using the chain rule. So my partial with respect to y is going to be that x is a constant multiple, it just hangs out. The derivative of some stuff to the negative first is -1 times my stuff to the negative second times the derivative of the inside, which is -1. Right? The derivative of x is 0, derivative of negative y is -1. Simplifying this, x times -1 times -1 is positive x divided by x minus y squared. Or maybe x times x minus y to the negative second. There are good reasons to use either one. It kind of depends on your preference. Yeah. Let's look at fxx. So when I'm doing this, I'm thinking about using this. I'm taking the derivative of that with respect to x. And I really think it's going to be nicer to write it like this because it just is, right? This, I could use the quotient rule, but part of it's going to be 0. So if I don't have to use the quotient rule, I kind of try not to. So let's see, that negative y is going to stick around. And then the derivative of some stuff to the negative second is -2 times my stuff to the negative third times the derivative of my stuff, which is just 1. I might simplify this as positive 2y over x minus y cubed. In a similar way, we're going to find fyy. So I'm going to take this part here, and then we're going to take the derivative of that with respect to y. So let's see, the x hangs out, and I'm going to get a minus 2 times x minus y to the negative third times a negative 1. And I'm going to simplify that as well. It's going to be a positive 2x over x minus y cubed. And then for the mixed partial. So again, I know I said this last time, I want to say it again. When you're finding the mixed partial, it's not going to matter which one you find. Whether it's fxy or fyx, they should be the same. But your work should still indicate the right thing. Meaning, if I'm finding fxy, I'm doing the derivative with respect to x first, and then the derivative of that with respect to y. So I'm going to write that as the partial with respect to y of what my fx is. This is saying I did the derivative with respect to x first, and then I'm going to do it with respect to y next. So that's going to be the derivative with respect to y of, here's my fx. It's negative y over x minus y squared. And I'm writing it that way because I do intend to use the quotient rule here instead of using like the product and the chain rule. So let's see what we get. We get the bottom times the derivative of the top, which is negative 1, minus the top times the derivative of the bottom, which is 2 times x minus y to the first times the derivative of x minus y, which is negative 1, all divided by x minus y squared, which is x minus y to the fourth. When your denominator starts off being raised to a higher power and you're using the chain rule, the quotient rule, it's always going to be the case that that factor shows up kind of everywhere. Specifically here, I can factor out an x minus y from this first term and the second term. So I'm going to rewrite this as x minus y times, here I'm going to have a negative 1 times x minus y. And here I'm going to have a minus times a minus y times a 2 times a minus 1. See, a minus is a minus 2y. All over x minus y to the fourth. One of those x minus y's cancels with that one. And I'm left with the denominator of x minus y cubed and the numerator of minus x plus y minus 2y, which just becomes minus x minus y. Couple things to point out. Nothing cancels here. I don't have an x minus y over x minus y. I have a minus x minus y over x minus y cubed. The other thing to point out is if we did it the other way, which we're not going to do, but if we did it the other way, so if we did fyx, which would be the partial with respect to x of our fy, which was x over x minus y squared, you should, when you have a moment on your own, take the time to verify that this is in fact equal to negative x minus y over x minus y cubed. They're definitely the same, but it's good to check. Yeah, there are other words I want to say about that. I guess the word I want to say is when you're doing the mixed partial derivative, even though it turns out the same either way you do it, make sure you do it the right way. Meaning, if you're supposed to find fxy, you need to do the derivative with respect to x first, and then the derivative of that with respect to y second. Don't accidentally do this one and get the same answer, even though it's probably fine. You want to do it the right way so that if someone's checking your work, they can see that you actually did the right one first and the right one second. Also, as usual, you're always welcome to ask questions. If you've got them, don't hesitate to chime in, or if you think I made a mistake, let me know. I don't think I made any mistakes here, but just, it's possible, right? Yeah, let's look at one more example of partial derivatives, and then we'll start talking about linearizations and tangent planes. So let's say we had a function of more than one variable. Let's say we had f of x, y, z equal to x to the fourth times sine of e to the y squared z. We want to find all the partials, meaning we want to find del f del x, we want to find del f del y, we want to find del f del z. Or basically all the partials until you've exhausted all the variables in your function. Well, del f del x isn't too bad. I've got x to the fourth times a constant. Sine of e to the y squared z, just a constant in this context. So del f del x is going to be 4x cubed times all the other stuff. That's it. On the other hand, del f del y is a little more challenging. I'm thinking of now x to the fourth times sine of e to the y squared z. In this case, I'm thinking of this is a constant, and so is that. So I'm kind of thinking of something like 6 times sine of e to the 3y squared. That's kind of what I'm imagining I'm taking the derivative of. When I take the derivative of that, the 6 is going to hang out. I'm going to get the derivative sine of some stuff, which will be cosine of the stuff times the derivative of the stuff. So you don't have to actually plug in numbers, but I find it really helpful. It just makes it work for me. So I'm thinking, okay, this x to the fourth is going to hang out. And the derivative of sine of some stuff is cosine of the stuff times the derivative of that stuff. I have to use the chain rule again, because the derivative of e to something else is e to the thing times the derivative of the thing. So the derivative of e to the y squared z is going to be e to the y squared z times the derivative of y squared z. What's the derivative of y squared z in this particular problem? Exactly, 2yz, because we're taking the partial with respect to y. Del f del z is going to be virtually the same until we get to the very end. That x to the fourth constant is still going to hang out, and the derivative sine of some stuff is still going to be cosine of the stuff times the derivative of the stuff. So we're going to get cosine of e to the y squared z times the derivative of e to the y squared z. It's just this time, the derivative of e to the y squared z is going to be e to the y squared z times the derivative of y squared z. But this time that's going to be y squared. So right here, we have the derivative with respect to y of y squared z. And right here, we have the derivative with respect to z of y squared z. Same process, just different variable. And I didn't see him talk about or assign any problems that had implicit differentiation in them yet, so I think we'll skip that for now and maybe come back to it later. I did want to just mention real quickly. So I think someone had mentioned that problem 44 from the homework seemed especially challenging as well, because it had like just a lot of kind of weird funky variables in it. Let's take a quick look at that one, and then we'll talk about tangent planes. So here's problem 44. I'm going to read it. If an antibiotic is administered to a patient at a constant rate through intravenous supply and is metabolized, then the concentration of antibiotic after 1 unit of time is, so we've got the concentration at theta comma v. I don't know what theta and v stands for yet. We'll figure it out. The concentration is given by C0 times e to the -1 over v plus theta times v times 1 minus e to the -1 over v. That looks gross. It's not that gross. It just looks gross. And they're giving us C0 is the initial concentration. You know what I read when I read that? C naught is a constant. That's the important thing to take away from there. There might be more, but that's certainly probably the most important thing about that. What else? Theta is the rate of supply. Clearly a variable, both in that they're telling us it's something that's changing, and also it's one of the things that your function depends on. And what else? They're telling us that V is the volume of patient's blood. All right. So let's find d, c, d theta. I'm going to leave dc, dv for you to, sorry, I should say del, not d. Let's find del c, del theta, and I'm going to leave del c, del v for you all to find out. So from this first part, are there any thetas in there? No. So the derivative of that first part, 0. From the second part, this problem is actually really easy when you do it for theta. The v part's definitely the harder. I think maybe we'll address the v part. So it looks like I've got theta times a constant, and the derivative of theta times a constant is the constant. So the partial with respect to theta is maybe almost a little too easy. I mean, not really. It's still challenging. We have to think about it. The partial with respect to v is going to be a bit harder. If I was doing the partial with respect to v, I would probably make a couple changes. I would probably rewrite my function in the following way. I would write this as c naught e to the, instead of -1 over v, negative v to the -1. It's going to make it easier for me to use the chain rule. Over here, I'm probably still going to write it as theta times v times 1 minus, again, e to the negative v to the -1. So if we start taking the partial with respect to v, constant hangs out. What's the derivative of e to the stuff? There's a very general answer I'm looking for, which is that the derivative of e to the stuff is e to the stuff times what? Thank you. It's exactly what I was hoping for. Right. So we're going to have e to the this times the derivative of that. Now it looks like over here, in addition to the chain rule, what other rule are we going to need to use? Well, I've got v times another function of v. I'm thinking I'm going to have to use the product rule. And I'm going to think of this as kind of one piece and this as another piece. So when I write my derivative, it's going to look like f prime times g plus f times g prime. The g part is easy to fill in for. It just is the same thing it was before. And the f part's easy to plug in for. It's just the same as it was before. What's f prime going to be? What's the derivative with respect to v of theta times v? Good old theta. And this part here, I'm going to leave for you all to fill in, so I'm not actually doing the whole. But I think you can get it from there. So a lot of these problems, especially the wordier problems, and especially in 17C, a lot of it's just taking a minute to figure out what is what. What's a variable? What's a constant? What am I differentiating with respect to? If they'd written this as 5 times e to the -1 over x plus y times x times 1 minus e to the -1 over x, it probably would have been a little bit easier to tackle because they're variables we're used to seeing. Don't let new variables, or maybe not even new, don't let different variables kind of put you off. They're really not that bad. And if you want, if it makes it easier, you could totally rewrite this. You could say, I'm going to make this easier for myself. I'm going to say c of xy equals c naught e to the -1 over x plus y times x times 1 minus e to the negative 1 over x. That helps. You can do it that way. And you can take the derivative with respect to either variable, and then kind of, you still should write the answer with the right variables. So like if you do this, I don't really recommend it, but if you do it, you take the derivative with respect to x and then plug back in theta for x and v for y. Or if you take the derivative with respect to y, then you plug back in theta for x and v for y. It's definitely going to take more writing time, but it can help to see what's happening. You keep looking at that clock like it matters, because it definitely is not moving at all. It's been 6:44 for quite a while over there. All right. I think that was, yeah, we can look at that one some other time. So let's talk about linearizations and tangent planes. Linearization is something you definitely did cover in 17, or should have covered in 17A. But let's revisit it real quickly. So if I wanted to find a linearization of, say, y equal to f of x, it's really just a fancy word for the equation of the line tangent to y equals f of x. Often we like to give a little more information. We like to say we're going to do it at x equal to a, or you could say at a comma f of a. And the way we do that is y minus the y value equal to your slope times x minus the x value. I made a small error there. It should be y minus f of a, not f of x. Sometimes we draw a picture for this. I mean, we can think about our function looking something like this. And then we're saying at this point, we want to find the equation of the tangent line. Oh, well, we know how to do that. It's y minus the y coordinate. Oh, that's f of a equal to the slope. I'm really just writing the same thing again. You shouldn't write it down again. It's the same thing. There's our slope. There's our y coordinate. There's our x coordinate. Usual point slope formula of the line. And then to make it a linearization, I wrote the wrong thing again. I wrote f of x instead of f of a. Apologies. To make it a linearization, we solve for y. So the linearization is a function of x, and it's L of x equal to f of a plus f prime of a times x minus a. For example, let's say we wanted to, let's use a piece of paper, so much space. Wasting all that space, but it really does call for a piece of paper. Let's find the linearization, fancy word for equation of a tangent line, of the function f of x equal to the square root of x at a equal to 9, and then use it to approximate the square root of 10. Square root of 9 is, so usually when what you're doing with these linearizations is you're picking a point that's easy to substitute into the function, and then you're using it to kind of estimate the function value at a point that's harder to plug in. I don't know what the square root of 10 is. I definitely know what the square root of 9 is. So I like to draw a picture. It's kind of the same picture I just drew. The idea is, here's 9. Here's the tangent line at 9. Kind of a little off there, it's all right. And then the idea is we're going to plug in 10. But instead of plugging it into the square root function and getting out the square root of 10, we're going to plug it in to the linearization. And we're going to actually be able to calculate that value. And the idea is that that value is close to the value that we want. It's an approximation. So let's do all the things. Our function is the square root of x, or preferably x to the 1/2. Our derivative is 1/2 times x to the minus 1/2. Or if you like, 1/2 root x. And then we actually have to plug in the value we're interested in, right? I don't just want to know the function, the derivative anywhere. I want to know what the function and the derivative are at this point, because I want to know the y value and I want to know the slope. So f of 3, sorry, not f of 3, f of 9 is the square root of 9, which is 3. And f prime of 9, which is my slope, is 1/2 times the square root of 9, which is 1/6. So my equation of my tangent line is y minus the y value equal to my slope times x minus the x value. Or solving for y equal to 3 plus 1/6 times x minus 9. Usually I'm of the opinion you don't want to simplify this any further. I definitely saw Dr. Liddell simplify his linearization in class. That's also fine. But multiplying this 1/6 through and combining these is not really going to help me in a reasonable way. You could totally write this out as y equal to 1/6 x minus 9/6 plus 3 is going to be plus 3/2. That doesn't really tell me anything more than I already knew. And it definitely doesn't help me plug in 10. If I'm trying to approximate the square root of 10 with my linearization equal to 3 plus 1/6 x minus 9, I think it's much easier to plug in 10 here than it is to plug in 10 here. It's not, I will say, this example, it's not like that much easier to plug in 10 in either one. But in the next example, you'll see it is easier to kind of leave it unsimplified. So that means for us that the square root of 10 is approximately this function where we plug in 10, which is 3 plus 1/6 times 10 minus 9, which is 3 plus 1/6, which as a decimal is 3.166666 forever, or as a fraction would be 18.6 plus 1/6 is 19.6. Just for comparison, if you actually plug in square root of 10 to a calculator, square root of 10 is approximately 3.1622. And it doesn't stop there, but so our estimate's pretty good, right? We did a good job of estimating the square root of 10 without ever having to use a calculator. Cool. So here's the idea. In 2 dimensions, we can linearize a function with the tangent line. In 3 dimensions, we can linearize a function that's, bless you, that's a surface with a tangent plane. So instead of touching, right, the function at one point being a line, we're going to touch, right, if this is like our surface here, we're going to touch this surface. We're going to touch the surface at like one point, and at that point, maybe I can, we'll see if I can do this. At that one, wow, man, it's hard. At that one point, right, the tangent plane is going to touch that surface and be an approximation of that surface near the point that it's touching. Right? If you move far away, right, you can see there's a lot of difference far away, but near the point it's touching, they're a pretty good approximation of each other. So that's the whole idea. We're just extending this to another dimension. And nicely, the equations are kind of the same. They just have extra pieces. So yeah. So let's say we want to find or write the equation of the plane tangent to the surface z equal to f of xy at the point. I usually write x naught, y naught as is your book, but Dell likes to write AB, so I'm going to do that. Again, this is the linearization. of z equal to f of x, y at the point a comma b. And so the idea is, right, we've got some surface, and at some point, we're saying we can find, let me draw this a little bit more in a way that I can actually draw the thing I'm trying to draw. Basically, we're saying there's some plane here tangent to the surface. It's doing kind of this thing. My picture's okay. It's not great. There's better pictures in the book. That's why, right, you've got the book, you can look at the pictures. It's definitely one of the things it's good for. But that's right, this plane's kind of just sitting on the top of this surface, tangent to it. And we're trying to find the equation of that plane. So we're going to do the same thing. Instead of doing y minus the y coordinate equals your slope times x minus the x coordinate, we have to kind of do two pieces. It's going to be z minus the z coordinate equal to, it's not just one slope. In fact, there's actually two tangent lines we care about. There's the tangent line in the x direction and the tangent line in the y direction. So we're going to have the slope in the x direction at the point times x minus the x coordinate plus the slope in the y direction at the same point times y minus the y coordinate. It's very much the same idea. And then if we want to rewrite it, we can write it as the linearization of your function equal to f of ab plus fx of ab times x minus a plus fy of ab times y minus b. And I will mention there are some, I think there's one or two homework problems that actually have you do a linearization of a function of more variables. You're just adding, so like if your function was a function of like x, y, and w, you would throw on another partial with respect to w at the point times w minus whatever the third coordinate was. I will do an example like that on Wednesday, but I'm not going to get to it today. So let's look at an example. Say we want to find, so let's say we want to find the linearization of, what do I got here? F of x, y equal to x to the fourth y cubed at the point 1, 2. And then we're going to use it to approximate, what have I got here? F of 1.1 comma, F of 1.1 comma 2.3, which would be 1.1 to the fourth times 2.3 cubed, which would be easy to calculate with a calculator. Probably not terribly impossible to calculate by hand, but certainly not fun, right? 2.3 cubed, 1.1 to the fourth, also kind of terrible. But we're not going to do that. We're going to approximate it. So we need to find the partials. We need our fx, which is going to be 4x cubed times y cubed, and our fy, which is going to be x to the fourth times 3y squared. And we actually need is those partials evaluated at the point of interest, meaning I need fx at 1, 2, which is going to be 4 times 1 times 8, which is 32. I need fy at 1, 2, which is 1 to the fourth times 3 times 2 squared, which is 12. And I also need to know what I get when I plug it into the original function. So I need f of 1, 2, which is 1 to the fourth times 2 cubed, which is 8. I have all the pieces now. I just have to throw them into this formula. So my linearization of this function of two variables is going to be my f of 1, 2 which is 8, plus my partial with respect to x, which is 32, times x minus the x coordinate, plus my partial with respect to y, which is 12, times y minus the y coordinate. And now, personally, I would choose to leave it like this, especially if I'm going to have to plug in 1.1 and 2.3. I'm going to find it much easier to plug in 1.1 to this than, well, in fact, let's simplify and see what it would be. If you actually simplify this out, you would get the linearization equal to, let's see, I'd have a 32x, I'd have a 12y, and I'd have an 8 minus 32 minus 24. That'd be, let's see, 8 minus 32 is negative 24, minus another 24 is minus 48. And at least to me, it seems much easier to plug in 1.1 for x and 2.3 for y in this expression. Right, plugging in here, 2.3 times 12 is a little bit of mental work. 1.1 times 32 is not that bad, but like it's just going to be easier here. So when I plug in 1.1 and 2.3, I get 8 plus 32 times 1.1 minus 1 plus 12 times 2.3 minus 2. And that's going to give me 8 plus 32 times 0.1 is 3.2. And 12 times 0.3 is going to be 3.6. So I end up getting 8 plus 3.2 plus 3.6, which is going to be 14.8. If you did actually take this and plug it into a calculator, you would get approximately 17.81. So our estimate's all right. It's not like great, but it's better than, so like, to be honest, if I was doing this without doing this, like if I was like, if you plugged in 1.1 and 2.3, what would you get? I probably would have guessed something a lot closer to 8. So I've been like, oh, well, 1 to the 4th times 2 to the 3rd is 8. And I'm not that far away from 1 and 2, so 8 seems like a good guess. It's not, right? 8's not a great guess. 14.8 is a much better guess.